Hey there! Have you ever wondered how my cochlear implants work? They're powered by some truly amazing communication technologies. And you know what? Being out here in this peaceful camping spot makes me appreciate them even more. It's like they connect me to the sounds of nature, the crackling fire, and your voice. Let's dive in and learn about them together. Welcome to our video on pulse modulation and multiplexing, two fundamental concepts in communication systems that have revolutionized how information is transmitted in our modern world. Whether it's enabling efficient data transmission or playing a key role in technologies like cochlear implants, these principles have a profound global impact. Let's dive in. To begin, let's understand pulse modulation. This process refers to how we encode analog signals into digital pulses so they can be transmitted efficiently. Specifically, we take samples of the analog signal and convert them into a sequence of digital values. The term that describes this specific step is called quantization. Quantization works by assigning discrete values to the samples, effectively transforming them into digital data. This is a key process in digital audio and communication systems. To simplify, imagine snapping a picture of a moving car at regular intervals. These snapshots are like the samples we take during quantization. But how do we decide the rate at which we sample the audio? This is where the sampling theorem comes in, defined by Harry Nyquist, who established that the sample rate must be at least twice the maximum frequency of the signal's bandwidth to accurately reconstruct it. Think of it like trying to capture the motion of a car. If you take too few pictures, you'll miss the details. Sampling at twice the signal's maximum frequency ensures we don't miss anything important. Another important concept is bit depth, which defines the number of bits of information in each sample thero. Higher bit depth increases the dynamic range of audio, resulting in clearer and more detailed sound. Imagine it as having more colors in a painting. It makes the picture richer and more realistic. Let's explore some fundamental principles that make modern communication systems so effective. First, there's time division multiplexing, TDM. TDM divides a single communication channel into multiple time slots, with each slot allocated to a different call. Think of it like sharing a highway where each car gets its own lane for a few seconds. Then there's pulse code modulation, PCM, a process used to convert analog voice signals into digital signals. PCM involves three key steps. 1. Sampling. Measuring the amplitude of the analog signal at regular intervals, Nyquist theorem applies here. 2. Quantization, rounding each sample to the nearest value within a finite set of levels. 3. Encoding, converting quantized values into binary format. Finally, we have digitization of voice, which transforms analog voice signals into digital data for processing and transmission. This offers several benefits such as better sound quality with no degradation over distance, easier integration with digital systems and the internet, encryption for secure communication. Now let's move to multiplexing, which refers to the sharing of a communication medium by multiple signals or devices. Imagine several lanes merging into one highway. That's what multiplexing does for signals. One common type is time division multiplexing, where each signal gets a specific time slot to use the shared medium. This technique is widely used in telecommunications and even in modern devices like cochlear implants to transmit different frequency signals to the brain. The global impact of these technologies is immense. Pulse modulation allows for efficient digital communication, while multiplexing optimizes the use of available bandwidth. Together, they power everything from high-speed internet to telecommunication systems. These advancements have improved work efficiency, flexibility, and reduced costs. However, they also raise important engineering issues. For example, ensuring the safety of cochlear implants is a top priority. Engineers must design systems that avoid nerve damage while maximizing hearing enhancement. Legal and cultural considerations are also critical. For instance, regulating medical devices like cochlear implants involves strict safety standards. Culturally, some communities may view these devices differently, emphasizing the need for inclusive and ethical engineering practices. Before we wrap up, let's briefly touch on amplitude modulation, where the amplitude of a carrier wave changes according to the modulating signal. Similarly, in binary phase shift keying, a continuous wave with no phase change, such as this binary that consists of ones or this binary that consists of zeros, represents digital signals. Techniques like these are integral to modern communication systems. In quadrature amplitude modulation, two carrier waves are modulated by varying their amplitude and phase, enabling the transmission of more data in a single signal. Analog communication systems consist of key components like a modulator, demodulator, and transmission medium. These systems laid the foundation for the digital technologies we use today. Pulse modulation and multiplexing might seem like technical jargon, but they're actually the quiet heroes behind modern communication. Whether they're powering cochlear implants or helping global networks stay in sync, these technologies keep us connected in ways we often take for granted. By efficiently and reliably transmitting data, they ensure that vital sounds, messages, and moments are always shared, making our world a little smaller and a lot more connected. I want to thank each and every one of you for being here today. Your interest, enthusiasm, and support make it possible for us to explore and celebrate these innovations together. Thank you for joining me on this journey.